Hello everyone, welcome back to my channel. So today we're gonna go over the statistics problem for controls, and basically let's read through the problem first. Acme ball bearing just completed a batch of 1 billion 2 millimeter ball bearings. Unfortunately, the diameters vary widely following a normal distribution with a mean diameter of 2.002 millimeters and standard deviation of 0.005 millimeter. So what percentage of ball bearings do you expect to have a diameter within the acceptable range of 1.998 diameter is between 1.998 and 2.002 millimeters. So basically they have 1 billion 2 millimeter ball bearings. And the diameter is very from oh, okay. The mean is 2.002 millimeters. So what percentage? Okay, so let's first draw a diagram. It's always helpful to draw a diagram of the normal distribution so that we know what we are working with. So the population size is two 1 billion, and the mean is at 2.002 millimeters. And the standard deviation is 0.05 millimeters. So the standard distribution, I know it looks bad, but it looks like that. So what percentage of ball bearings we expect to find within this acceptable range, which is actually from this location over here to uh this location over here. So we want to find the probability under this curve. And first, in order to do that, we have to find some z-scores, and we have to find the area under this curve in terms of decimals and then convert it to a percentage form. So our first z-score is going to be, let's call this z1. Let's call this z2. So the z-score for the mean is always going to be 0 since I think it's going to always be 0, but let me double check. We have equation sheet here. Actually, I don't believe it's on the equation sheet, but basically the z-score, general equation for z-score is going to be the x, which is the statistic minus the mean over the standard deviation. So our x value at 2.002 millimeter is going to be equal to the mean. So it's going to be 2.002 millimeters. And the mean is going to be equal to 2.002 millimeter. And then the standard deviation is going to be equal to 0.005 millimeter. So the z-score is going to be equal to 2.002 minus 2.002 over that, but that's equal to 0 over 0.005, which is 0 for z1. And now for z2, it's going to be equal to basically z2 is going to be from this 1.998. So 1.998, because basically this location over here is 1.998 millimeters. So 1.998 minus the mean, which is 2.002 over the standard deviation, which is 0.005, is equal to, let me see, is equal to 1.998 minus 2.002 divided by 0.005. So that z-score is actually going to be negative 0.8. And now we're going to use our z-table to first, how do we find this area? Well, it's going to be this big area over here minus, uh, or rather it's going to be, yes, that big area over there, basically this big area over here minus this area over here. And basically when we find a statistic value from our z-table, it gives us the area to the left of the curve. So let's look at our z-table. So basically, z1 is going to be equal to 0, and of course, let me see. Yes, so at 0, 0, So actually, this z-table is a little different than our normal z-tables since it gives you the probability from negative z to z. Um, it's a little different than a normal z-table, and I'll show you what a normal z-table looks like. This is what a normal z-table looks like. You'll notice that at the z-score of 0, we have 0.5, which is the area under the curve, and that is expected. But for our uh table back here, we will notice that the z-score probably is given from negative z to z at the bottom. So this requires some modifications. And also I discovered that this Gaussian distribution is I kind of drew it wrongly. So basically it should be normal distribution of z-scores. So basically over here, wait, why is it moving like that? But over here we have z-score of 0. And over here, which is the 1.998, we have a z-score of negative 0.8. And this is the area under the curve we want to find. So we basically want to find the probability, which is P, wait, P? Yes, P from x1 less than x less than x2. And this is gonna be the probability of 1.998 less than x less than x2, which is going to be 2.002. And basically this equates to a probability between the z-scores of negative 0.8 uh less than z less than 0. So as you see over here. So let's think about how to find this sort of probability. So the probability at each value at each z-score gives us the probability between two z-scores. And what this gives us is, for instance, if we're thinking about the probability at 0.8, we're going to have probability from negative 0.8, negative 0.8 to 0.8. So this will give you this area under the curve. However, we only need half of this probability, which is only this portion. Uh, so what we're going to do is the probability from negative 0.8 to z to 0 is going to be equal to the probability at z-score equal to 0.8, and we're going to divide that probability by 2. So if we can find 0.8 at our diagram, at 0.8, the area is going to be 0.5763. So basically, we're gonna have probability 0.8 to 0.8 and then divided by 2. So this is equal to 0.5763 divided by 2, and this is equal to a probability of uh 0.28815. And in percentage, we multiply it by 100%, so it's 0.28815 times 100%. So it's equal to 28.8%. So we're going to choose 28.8% as our final answer. I hope this video was helpful for you guys. I'll be posting these slides afterwards. See you guys next time.